In the last lecture, I introduced this chapter of aqueous ionic equilibrium. And so what that deals with is aqueous solutions and their species in it, right? So this goes back to chapter 8 and some of the fundamental understanding of ionic compounds and their solubility and what happens in solution when these molecules and ions or compounds interact with water. And that's important, and it's the foundation for us to grasp what buffers are and how we can calculate their pHs, right? So before I do calculate the pH of this buffer, which is a mixture of a weak acid here, this is acetic acid, and sodium acetate, which is an ionic compound that contains the conjugate base of the weak acid. And that here is the key. So before I calculate yet another pH of a buffer, let's review that a little bit and make sure that we're all on board. So first of all, we have a weak acid here. And you can look this up on the table with the Kas and the pKas and the equilibrium constants and all that, which is what the Kas are. So what that means is we have a reaction of this acid here with water. And that's usually how we write it. To form, that's going to have to go away, to form hydronium ion. So this hydrogen is transferred to the water and forms hydronium ion, which is what drops the pH. So we know this is an acid, it's going to drop the pH. But what it produces is a conjugate base. And that relationship between a weak acid and the conjugate base of that weak acid, that's important. And so we have the C2 H3O2 minus acetate, whichever way you want to draw it. And so that acts as a base. So we know because of this arrow here that this is not a reaction that goes to completion. We still have acetic acid and acetate and all of those reactants and products present in certain concentrations. So we give this an equilibrium constant, and because this is an acid equilibrium, we give that a Ka. And you can look that Ka up here, right? This is just a truncated little table. You find the acetic acid. Okay, here's that equilibrium we just wrote, and here's a Ka. Now, there's a relationship between the Ka and the Kb of the conjugate base. So this is what I was talking to you about. Understanding that these two work together. So that if you have a source of this conjugate base, and that could be any ionic solid that you dissolve in water, will produce acetate ions. And we know from the solubility rules that acetate compounds are soluble. Sodium acetate, magnesium acetate, ammonium acetate, iron acetate, all acetates are soluble. And so if you have a 0.100 molar solution of any acetate, what that means, let's just use sodium acetate for ease, but that doesn't matter. C2H3O. What that means is we don't have any sodium acetate in solution. None. Zero. Unlike a 0.1 molar solution of acetic acid, where we have a lot of acetic acid in solution. This is a soluble ion. Every single one of those molecules, ionic compounds, is going to break apart into sodium ions and acetate ions. Okay? So if I write here that I have 0. molar solution of sodium acetate, that means I have 0.1 moles of acetate in 1 liter of solution. Every single one of those. But if I have a 0.2 molar solution of acetic acid, I don't know, because I don't know how much of that breaks apart into ions. So, but the relationship between the conjugate base and its acid is important. So I can make a buffer by using this here, some of that acid, a certain amount of it, and adding a source of the conjugate base. That's that relationship. I can do that with any of those, right? I can do that with benzoic acid. So I take a mole of benzoic acid, and then I find myself benzoate. This is the conjugate base here, right? So weak acid conjugate base relationship. I find myself some of it, a source of it, calcium benzoate or whatever, and I have myself a buffer. And that's all it is. So if I go back to this here now, so this is the Ka, I can look it up, it's 1.8 times 10 to the minus 5, is it 5? 5? Yes, 5. Anyway, you can look that up. Then there's also a reaction of the conjugate base, C2H3O2 minus, which is, if this was standalone here, I would have 0.100 m solution of that acetate, right? Whereas I don't have that for this and the concentration. This would react with water to form acetic acid and hydroxide, okay? And this hydroxide that's produced will increase the pH, right? So we have this relationship that's extremely important. And if we mix the two, we can calculate the pH by just setting up an equilibrium expression or using the Henderson-Hasselbalch equation. Now, I will do this in a minute, but let me tell you, if this is a base and this is at equilibrium, then there's some sort of Kb associated with that. And so the relationship of the Kb, the way you determine that is with this, the Ka times this equation times the Kb equals the Kw. That's the relationship between the weak acid and its conjugate base. By the way, you have that same relationship between a weak base and its conjugate acid. Like ammonia and ammonium, you can calculate the Ka of the ammonium ion from the Kb of the weak base, the ammonia. So if we can then calculate the Kb simply by taking 1.00 times 10 to the minus 14 divided by the Ka, which is 1.8 times 10 to the minus 5. And so this gives me, I'm gonna have to look that up, 5.56 times 10 to the minus 10. Okay, not that we need it for this calculation, but this relationship, as I said, is important. All right. So now we can calculate again for the second time the buffer via two methods, the ice table or the Henderson-Hasselbalch equation. Now eventually you'll just use that Henderson-Hasselbalch equation because it's just easier. And but I still want to work that ice table one more time. Okay. By the way, this is the highlight of my career, to show you how to calculate buffers. It is so fascinating. You'll love it. Just you'll love it. Don't click and get a beer. Just stay with me. Watch me calculate this, okay? And then after, I'll tell you why it's so fascinating. So we have this equilibrium, and I'll leave out the water because the water is a liquid and it's not even part of the equilibrium expression, right? So I'll leave it out and focus on just say H plus and C2H3O minus, which is the acetate here, and so understand that the H plus is representative of the hydronium ion concentration. And so if we initially have 0.200 m of the acid, I'm given that. I don't know what the volume is, it doesn't matter, it's already a mixture. So we know that's going to shift to the right. So that's going to then shift to the right. But we also have, so we have none of that except for the ion, the autoionization, but we'll just, that's 1 times 10 to the minus 7, that's small. So initially we're gonna just say this is 0. But we have acetate because every single one of those molecules, ionic compounds, those units will break apart. And so we initially have actually 0.100 of acetate. And so then that's going to shift. This is going to increase by x, and this is gonna add by the amount of x, right? Because there's a 1-to-1 relationship. So at equilibrium, we then have 0.200 minus x. This goes up by x, and this is what we want to know. We want to know the concentration of x or hydronium so we can get the pH, because that's what I'm asking for. And then 0.100 plus x. I plug that into my equilibrium expression. 1.8 times 10 to the minus 5 equals x times 0.100 plus x divided by 0.200 minus x. We're going to assume that x is very small. This is only going to shift a tad to the right. It's a weak base with a low equilibrium or small equilibrium constant. So if we assume that this goes to 0, our calculation becomes a little simpler, and so we have 1.8 times 10 to the minus 5. We're going to multiply by 0.200, and we're going to divide by 0.100, and I get a x concentration of x, or the factor of x, which is in this case the H plus concentration, 3.6 times 10 to the minus 5. And so the negative log of that would be equal to 4.44. So the negative log of the hydronium ion concentration, which happens to be x in this case, is 3.65 times 10 to the minus 5. And you can take that and divide it by 200, and you'll get that this is a very small portion. So we can, and that justifies our approximation. You do not need to use the quadratic equation. I don't know about you, but I prefer that. And so what's fascinating about that? Absolutely nothing. I just thought I'd say it so maybe you continue watching. And there's a different way, an easier way to calculate that, and that's the pH is equal to the pKa plus the log of the conjugate base over weak acid concentration, which in this case is acetate and acetic acid. And so the pKa, you simply take the negative log of that 1.8 times 10 to the minus 5 of the Ka. So the pKa happens to be 4.74 in this case. So we can say that the pH equals the pKa plus the log. And so the base concentration is 0.100, and the acid concentration is 0.200. Remember, if these two concentrations are equal, the log of 1 is 0, and then the pH is equal to the pKa. That's also something you might want to remember. Later on for titrations, this is going to come in handy. So once you calculate that, you get a pH of 4.44. So I know I talked a lot and had a lot of theatrical moments there, but I promise you for the third lecture I'll stick straight to the point and just work problems. So continue watching.